In this video, we'll be working through some of the initial sections of Chapter 6 from your textbooks. This is called Basic Components of C. It starts with a simple outline. This is a general program outline, and it should match up with the very first program that we built in the previous video. Most programs follow the same outline, so you should be able to use this for any program that you create during this class. The header comment at the top, remember, tells anybody reading the program who wrote it, when it was written, and what it was written for. The statement with the pound sign and include tells the compiler to include the standard input and output library. And then all of our code goes in the main function because C is a compiled language, and the compiler will automatically look for main to start the program. So again, this matches up with the first program that we created. Here it is again. I've cleaned up a little bit of the comments since last time. So this is the header comment, who wrote it, what it was written for, the include statement to include the standard input and output library, the contents of the main function, and then main and the return 0 should look exactly the same as in the outline. So we can use this whenever we start a new function or a new program that we want to write. The programming process can be thought of as 4 simple steps. First, we edit the program, then we compile, then we execute or run the program, and if we're not fully satisfied with what we see, then we can return to step 1. The important thing about this is step 2. We can make changes to the program, but if we don't compile it, then those changes are not visible, they don't become evident. So let me show you what I mean. Here's our program, and if we compile and run, we'll see this print statement come into our run environment. It says, "Welcome to C programming." Okay, so now step 1 is to make changes. So we made changes, step 1, edited. Step 2 is compile. Step 3 is execute. So this way, since we followed the 3 steps, we see the changes that we made to that print statement. Okay, so now let's see what happens if we don't follow it. Let's say we make changes, like taking that statement back out, but we don't compile. If we go straight to execute, we can see that nothing has changed since the last time we ran the program. We have to recompile in order to see those changes. So we have to complete step 2, which is compile, and then run. And now the changes that we've made are evident in the run environment again. That's why you'll often see people use the compile and run or the build and run button so that it always does the same thing. We're always recompiling before we run, and that just ensures we don't skip a step. Let's talk a little bit about what programming is. A program is a set of instructions that can be translated into a language the computer can understand in order to perform a useful task. So those useful tasks all tend to boil down to the same thing: entering data, storing data, printing data, and manipulating data. There are pre-written functions for data entry and display. We've already seen the output function print format, so that's very basic. Data output will just be using printf for the most part. It's the data manipulation that's generally the hardest part of programming. But we won't be able to manipulate data until we know how it's stored. Computers, and therefore programming languages, have a standardized manner of storing information. Data is stored in a variable of a particular type. In order to store data in a C program, you have to store it in one of the 4 basic data types that I'm showing here. These are the most common ones, and they're the four basic ones. They're int for integers, char, C-H-A-R, for characters, floats, and doubles. So each of those types specifies the type of information that's going to be stored. Ints store integers, which are whole numbers. Chars store characters, which are letters, underscores, special symbols like exclamation points. Pretty much anything you can find on your keyboard can be stored in a character. Floats and doubles both store real numbers or decimal values, parts of a number. Floats have less precision than doubles. You can see that floats have about 6 to 7 digits of precision, where doubles have roughly 12 to 13. In order to create a variable or something that stores information like this, we're going to declare it. So this is what a declaration looks like in the C programming language. It starts with a type, one of those basic types that we just looked at, so that we can tell the compiler what type of information we'd like to store. And then we're going to give it a name. So here's a name that we can give to our variable. This one's called inches in foot, and it's of type integer. So it's an integer called inches in foot. And once we've declared it, we generally want to give it a value, which is called initialization if it's the first or the initial value for the variable. So here's an example of initialization. We've got inches in foot equal 12, because there's 12 inches in a foot, and ending with that semicolon. So this is also called an assignment statement, which we'll talk about in more detail later. These two things, the declaration and the initialization, can be done in the same step. So you can see here the data type, the name, the equal sign, and the initial value. So this is a declaration and an initialization together. And there are some rules to creating our variable names. You can see here that I wrote inches in foot with this underscore. And that's because one of those rules is that we can't have spaces in our names. So here's some of the other rules. We can only have letters, digits, or underscores. So we can't have variable names with other symbols in them. We have to start the name with a letter or an underscore. So you can't start it with a number, you can't start it with a digit. Names are case sensitive. So something that has capital letters in it will be considered distinct from something that does not. We can't use any keywords or reserved words. The compiler reserves some words because they mean special things. So for example, we can't create a numerical value called float. Float's a reserved word that indicates a decimal value, so we can't use that. Similarly, we can't create an integer called int. Int means something else. So some of the other reserved words are return, do, double, void, and in general, if you're working in the IDE, they change colors, and I'll show you when we switch back over. They look different because they're reserved words. And in general, we should choose a name that makes sense for the variable's purpose. So when we created an integer called inches in feet, we knew that it represented the number of inches in a foot. That's why it had the value 12. We're going to use that to create a simple program that calculates the number of inches in a mile. In order to do that, we're going to need something called the assignment statement. So kind of by definition, a variable has to have the ability to vary, to change. And so one way that variables change values is with the assignment statement. So you can see here this represents the general syntax, and I'll use these a lot. These triangle brackets represent anything that fits this particular characteristic. So this has VAR, which stands for variable, which means we can put any variable here. So any variable can go on the left side of the equal sign. Then there's an equal sign. On the right side, there's an expression. So an expression can be lots of different things. It might be a single value, like 12. It could be an arithmetic expression, like 12 times 4. We can include variables. It could be 12 times inches in foot. And we'll see some more complicated expressions as we continue to deepen our knowledge of C. So here in the example is some of our code for creating this program that figures out the number of inches in a mile. We have two variables. They're both integers, so we've got int inches in foot with an initial value of 12, and int feet in mile with an initial value of 5,280, and another variable called inches in mile, which we've not assigned an initial value to. Then we'll calculate inches in miles equal to the inches in a foot by the number of feet in a mile. And so this is an assignment statement where here's our variable. So inches in miles is the variable. Here's our equal sign. And here's our expression, the inches in foot times the feet in mile. And so it's very important that we follow the syntax. The syntax is the rules of the language. So all of our assignment statements are going to look the same. A single variable on the left-hand side, then the equal sign, then the expression. If we write it a different way, it won't work. All right, before we take this to the IDE, we need to know how we're going to be able to see the results. We've got all of the code, we now have this answer, inches and miles, but no way to show that to the user. Our print statements so far just print literal statements that we put inside quotation marks. So in order to print the value of a variable, we're going to specify the format of the variable that we want to print. So each of our basic data types has a corresponding percent code. So these are listed here. The code for an integer is %d. This stands for decimal, but it stands for decimal in the sense that we use decimal values or base 10 values, not decimals as in parts of a number. The one for characters is %c, the one for floats is %f, and the one for double is %lf, which stands for long float. So as an example, once we've created this final value for inches in a mile, since it's an integer, we're going to tell the print statement that we'd like to print an integer by putting the integer percent code in the print statement. And this tells it, I'd like to print an integer. And then we're going to specify which integer we'd like to print by putting a comma after the quotation mark, and then the name of the variable we'd like to print out. Okay, so we're going to take all of these things back to the development environment, and we're going to create a simple program that calculates the number of inches in a mile. So we're going to start a new program. We're going to go ahead and save it. If you don't save it as a .c, you don't see any of that syntax highlighting. We're going to go ahead and save it as inches.c. So remember, we want to save our programs as .c's. That's how we make sure that they are C programs instead of C++ programs. So here's inches.c. We're going to make our header comment. This program calculates the number of inches in a mile. So this is a multi-line comment. Remember, we're going to specify in our header comment who wrote it and what it was written for. And we have our preprocessor directives. Remember, the directive we need to have is to include standard input and output library so that we have access to that print statement. Then we'll make our main function. And we'll put all of the code that we've been seeing so far in main. So remember, C is a compiled language. The compiler will look for the main function for all of our code. So we're going to put everything in main. We're going to create a variable. Here's the number of inches in a foot. So this is our variable declaration. Remember, we start with the basic type, then the name, and then if we want to give it an initial value, we can follow that with an equal sign and the value that we'd like to give it. I'm going to do the same thing with the number of feet in a mile. Start with its type, then the name, then the equal sign, and then the initial value. We're also going to have our final variable, the number of inches in a mile, and we're using names that indicate what these variables are for. We're going to declare that one but not give it a value. We always put our variable declarations at the top of a function. That's so when we begin a function, we already know ahead of time all of the pieces that we have to work with. So in this case, we have 3 integers to work with. 2 of them have values, and 1 of them is our calculation for the program. So now we're going to use our assignment statement. We're going to set inches in mile equal to the inches in a foot times the feet in a mile. And you can see here the development environment is filling in those values for me. When you start typing, it'll try and guess which variable you mean. So here's our assignment statement. We'll set inches in miles equals to inches in foot times feet in mile. And then we're going to print our output. So you can see here I'm making comments for each major section of code. Comments are a good and necessary practice to get into. You have to have comments to describe what your code is doing. This is useful now so that if you go back to the program, you can remember what you're working on. If you're looking at one of my programs, you can see my explanations for it. But later on, if you go to work as a programmer, you'll need these comments in order to describe to your teammates what you were working on, and they'll do the same so that you can read their code. Okay, so now we're ready to print output. We're going to use that same print function. Now, instead of printing words to the screen, we want to print a value. So we need to tell it what type of value we'd like to print. We're going to print an integer value, and then we have to tell it where to get that value from. We want it to print the inches in mile, that value. And when we finish that, we'll be done. We want to end our main function with our return statement. Okay, so now we're ready to take a look. We're going to compile, check for errors, and then we'll be able to run it. So here's our run environment, and it does exactly what we told it to do, which is to print out an integer. So unfortunately, there's not a lot of context there for anybody else who runs our program. So they get a value, it's 63,360. So what does that mean? So we're going to go back in and add some context. We're going to say that the number of inches in a mile is blank integer value. So we can mix and match words and percent codes. We can say the number of inches in a mile is blank. This blank is an integer value that we're going to have the computer fill in by filling it in with this value that we calculated, the number of inches in a mile. So now if we recompile and rerun, then anybody who runs our program can get the full context. The number of inches in a mile is 63,360. It's a cool little program. Okay, So now I want you to give it a shot. Create a simple program that calculates the number of minutes in a day using the number of minutes in an hour and the number of hours in a day, and print the result to the screen just like I did with the number of inches in a mile. So give it a shot, and then you can look on the web course to see my solution to this practice problem. Good luck!